Molarity and stoichiometry, what we're going to be talking about is we're going to look, quick review of molarity, talk dilutions, and then go straight into titration and stoichiometry. Again, remember molarity is moles of solute per volume of solution. One of the things to remember about molarity, it is ultimately temperature dependent. So one of the things we'll be dealing with later on is we'll talk about molality and we'll look at things that are not temperature dependent. For now, it's irrelevant. We'll focus on strictly using molarity. One of the things you already know is that when you mix a solution, it's mass per unit of volume. We convert the mass into moles. That moles over the volume gives us our solution. Now, when we do a dilution, you remember this from your previous class, it's always the molarity times volume equals the new molarity and the new volume. So basic dilution, typically we associate this with going from a highly concentrated amount, so something like, let's say I have 12 molar HCl and I want something that's 2.5 molar and I need 500 milliliters of it. So a dilution is all about how much of my original do I need to produce the new. You can see these types of problems involving solving for the water, involving solving for the amount of your concentrated. You could even see it solving for what's the new molarity if this is the volume and this is how much I apply. It's basic algebra. You all remember this. Now, when we use molarity in stoichiometry calculations, we're still following our same rules. We need to get to moles. Molarity gives us that because molarity by definition, when we talk molarity, is moles per liter. So if I know a volume, I can get to moles because I simply cancel volume and I have moles. I then use my molar ratio from my balanced equation. And then if I need to solve for a new molarity, I simply get out of moles. And again, molarity will allow me to do that because if it's moles per liters, I simply invert that, multiply by the inverse, the moles are on the bottom, liters are on top, I solve for what I'm solving for. So you can use this any, a variety of ways, just like we would any basic stoichiometry calculation. Now in the titration, the main thing is recognizing what it is we're doing and how we're doing it. We have some form of an indicator to allow us to notice a change, and or we go by with some kind of a visual cue, whether it be an indicator in terms of acid base, it could be the loss of color if we're looking at a redox reaction. There's a variety of clues there for us, but ultimately it's that color change that allows us to recognize when we have hit the endpoint, when we have finished our reaction. Now, when we do this, again, as we talked about before when I said you can go, we're still following our same basic rules. You get a volume, you get to moles, coefficients, and out, and that's basically all we're doing. So, the practice problem. Here's your practice problem. What I want you to do is I want you to pause the video, solve A, start the video, look at the answer, pause it again, solve for B, look at what you do. Always compare what you do to how it should have been done and make notes about what was different. If there's something that you are confused with, make sure you bring it up in class. So to solve A, you should have immediately recognized it's a dilution, so it's M1V1, M2. As mentioned, we know this is basic algebra, so I solve for V1, so M2 times V2 over M1. So when we set it up, we get 6, 50, 16. You solve. Basically, you need 18.75 milliliters of the concentrated to produce the dilute. Okay, so now pause it again and go to B. First, you better double check and recognize you need a balanced chemical equation, so we know everything's 1 to 1. So when we set it up, we start with the molarity of our known. And the molarity of our known is we have the 6 molar, and we know it took 17.35 mils. So my HNO3 was my known. Then I want to go to the sodium hydroxide, and I need the molarity of the sodium hydroxide, which means I need moles over volume. So that's what I set up here. Now solve. So multiply by the top, divide by the bottom, and you end up with a molarity of 0.058. That's all there is to it.